phenomena. First, I would like to thank the organizers for inviting this talk, and I also acknowledge the contribution of the group members. I am the principal investigator of the group Quantum Nano Device Laboratory at ISER Bhopal, and I also acknowledge the funding agencies and IEEE for support. Here is the outline of my talk. First, I will give you an introduction on spintronics and magnetization dynamics. Then I will separate the talks in two parts. One is on spin devices, another is on spin circuits. So in the spin devices, I will be talking on multiferroic composites that has been very promising for energy efficient computing paradigm. And also I will talk about antiferromagnetically coupled nanomagnets that can be very area efficient and also fast. Then I will be talking about the experimental works that are going on, and then I will summarize the part. Then I will be talking about spin circuits, and that has been proved to be a very versatile tool for understanding and proposing experimental works. I will be talking about spin pumping, and particularly I want to talk on spin circuit representation of spin pumping into topological insulators. That's a recent work. That topological insulator has been also very competitive for energy efficient technologies, and then I will summarize the work. So in the first part of my talk, that is on spin devices, uh, I will be talking on these multiferroics and antiferromagnets. Then particularly I want to talk about experimental works where we will be talking on this fabrication and also different characterization of the materials and devices. In particular, I will be talking about ferromagnetic resonance that is useful for determining the damping parameter, and some nanoscale displacement measurements like in the nanometer dimensions for piezoelectric and magnetostrictive materials in multiferroics. In the spin circuit part, I will be talking on first the uh, benefits of having spin circuits, and then I will be talking some of the works that we have done in the some previous years. And in a recent development, I would be talking on these topological insulators that I was talking about. So I may not have time to go through all this part in the particularly the second part, but I will try to do some part covered here. Okay, so electronics, has been on electronics there has been a development over the past century, first half of the second half of the last century, and there was a Nobel Prize in Physics was awarded in 2000 for the development of electronics technology. Okay, but there are problems with the traditional transistors, particularly the energy dissipation and the process variation. So for that, for spin electronics, people have been looking into in this century. So the Nobel Prize in Physics also has been awarded for spintronics in 2007 for their works in back in 1988 on well-known giant magnetoresistance. So here in spintronics, we are using also spin rather than charge degree of freedom to store a binary set of information, that is say up and down, that may be encapsulated as 0 and 1, and they are separated by an energy barrier. So that is why it is also non-volatile. Non-volatile means even if power supply is taken out, the state remains. While for traditional transistors, you need to do several transistors to have this setup, right? So there has been several nanoelectronic paradigm that has been proposed for to replace the transistors, but the conclusion at this point that is accepted by academia and industry both, like for example a senior fellow from Intel, so say that the spintronics have a better chance in the future. And as you see that the research is going really up over the time on spin electronics. Particularly, they are going for Mars mission. They are putting it going for car in the car because their endurance is very high, so they last long. And different companies you can see starting from IBM, Samsung, Global Foundries, they are working on spintronics. So I'll give you a quick introduction on spin electronics. So here it is a rapidly developing technology. It can be used for store, process, and communicate information. And particularly, there is also inbuilt functionality like some brain mapping, neuromorphic computing that can be also very useful. This kind of device, but I will not be talking much on that today. So in spin electronic devices, there is no charge movement. So that's why there is no I current. So that's why there is no ohmic energy dissipation. But there is a dissipation due to magnetization damping, because inside a magnet, whenever spin rotates, switches from one direction to another direction, there is some work done. So because of this work done, there will be some energy will be deposited. But this is internal and quite small, right? But that is not the main energy dissipation. That has baffled the community for some time. The key issue is that there is a dissipation due to applying external quantity like voltage, current, field, whatever you want to apply. So for magnetic field, that was like first generation spin electronics, where people are applying the magnetic field, but it is very difficult to control at very small scale. Like there are billions of chip in the in our computer. So making all those things create a current carrying coil and create a magnetic field is very difficult to confine the electric field. So confine the magnetic field. So that's why people have in the next generation spintronics people have gone for like current and then the voltage. So that is what we are talking about today. That using voltage to switch the magnetization is a in a multiferroic composite. So there are many emerging spintronic devices. In particularly, we'll be talking about this first multiferroic composites, where it is possible to do the electric writing while magnetic reading using giant magnetoresistance or tunneling magnetoresistance mechanism. There are also single-phase multiferroic materials, antiferrometrically coupled magnets that I will also talk about today. There is also giant spin Hall effect like platinum, tantalum, those kind of materials. They can generate huge spin current applying while applying a charge current. And there are topological insulators, cadmiums, optical switching also is there, circular polarized light you can put to switch the magnetization in either direction. There is spin waves in magnetic insulators, and there are many other applications are also there, particularly one ultra sensitive sensor for magnetoencephalography, by which we can measure the tiny magnetic fields. That is also used for non-invasive brain mapping. Then there is neuromorphic computing. So there are several things that are coming along. So first, I will give you a quick introduction on the magnetization dynamics. That's why it is important. So one of the important things that I want to point out, that whenever magnetization is oriented at one direction, it is not static. It is rather fluctuating from the little bit of fluctuating it is depending on the barrier. If the barrier very is huge, then it will be fluctuating less, right? And whenever magnetization is switching from one direction to another direction, then there will be this stochastic nature of switching process will be coming into play, because particularly we want to devise the room temperature thermal fluctuations. So we do need to consider this thing. So this is well-known Landau-Lifshitz-Gilbert equation for magnetization dynamics. So here there is a precession term and there is a damping term alpha. So alpha is something that has to be determined experimentally. Also there are theoretical works, but this is a very critical parameter to determine to understand the magnetization dynamics. That also we'll be talking about today. And for performance matrix, this gives the performance matrix in switching delay and energy dissipation, because it gives you the understanding that how long it takes or magnetization to switch from one state to another. Now you need to include also the thermal field. So thermal field, room temperature thermal field, one needs to include, and this mean and variance of the performance metrics like switching delay and energy dissipation, that is what we get. So it is very important, because worst case scenario we need to be very prepared of. Okay, so clock speed in a computer depends on that, what is the worst switching delay that you have to tackle. Okay. So during the switching also, it dissipates the energy. One can calculate the energy dissipation, and this energy dissipation will turn out to be 1 attojoule. That is very precise, a very small energy dissipation, and that is equivalent to the energy barrier in between the switching states. But what we need to consider, that is what is CV square, because CV square is capacitance. So for any application of voltage we do need to consider CV square different kind of dissipation, or I square RT if you are switching by current. So voltage is more important because we can directly apply voltage, otherwise we need a current source to apply current, right? So we are talking about these voltage control devices here, and that for multiferroics we can show that is CV square, energy due to CV square is very small, and that's why it is energy efficient. So if you do a simulation, then stochastic LLG simulation, it shows that magnetization is fluctuating from 180-degree depending on the energy barrier. This 40 kT energy barrier is equivalent to 10 years data retention time. So it is quite industry standard. And if we do such simulation, we can see a very nice Boltzmann distribution. And we can also see the azimuthal angle. It is quite constant because it is a circular cross section, and it quite matches the energy barrier corresponding to Boltzmann distribution. It shows that our simulation things are understandings are correct. Okay, so now I'll come to spin devices. Okay, so here we are talking about multiferric composites. So here what happens is that we put an electric field along the piezoelectric layer, and it creates a stress or strain in the piezoelectric layer, and that gets elastically transferred to the magnetostrictive layer, and where it can generate a magnetostriction, and it generates a magnetoelastic anisotropy, and that anisotropy can counter the shape anisotropy energy barrier, and it can switch the magnetization. So research on multiferroics is also growing over the years. So it is a very promising area of research that we are following. So switching up spin is a very it was pointed out that in my paper that if only scientists can find a way to switch the bit of information with the minimal loss of energy, because we need to do better than the traditional transistors. So then only we will be able to switch. We will be able to put the spintronics in general purpose computers. Okay, so here are some of the works that we have done. That, for example, there is a switching delay energy trade-off. It shows that if the delay is increasing, energy dissipation is decreasing. That is the usual trade-off, and it shows that like less than 1 attojoule energy dissipation, it is possible at some nanosecond switching delay. So also we have shown that the input-output characteristics of this multiferroic composites, there is a high gain region like transistors, because high gain region is important for logic design, that how one device is connected to another device and still it can be worked out in that way. Then also we have worked on Landau limit of energy dissipation, that what is the minimum limit of the energy dissipation that is possible. And in that case, the switching delay may be high. That's fine. Particularly, it is useful for some places where battery replacement it is a problem, and we have to work with the harvesting energy from the environment. Also, there are some exotic cases where the polarization and magnetization, they are interface coupled. So polarization is down, magnetization is left aligned. Polarization is up, magnetization is right aligned. So those kind of exotic things also, they are helpful in the switching process. Now we have also worked on this energy efficient logic. For example, this is so-called Bennett clocking mechanism, where there is a dipole coupling in between the nanomagnets. So these are the nanomagnets. So but the dipole coupling is bidirectional. So we need to put the unidirectionality in time, so that the signal propagates one direction to another direction. So in this way, we can devise different computing platforms, computing gates like that. But there is a more promising idea one was proposed, that is using multiple contacts on a piezoelectric layer. If you could put multiple contacts, then the strain gets added and it elastically gets transferred. So it has been shown that they have the properties of concatenability, nonlinearity, feedback elimination, and gain. All the logic properties, critical logic properties they possess. And it has been shown also that universal logic gates can be also designed using this methodology. And there is a huge area advantage, because rather than using multiple elements, we are able to use single elements to devise the logic gates. Okay, so now scaling trends is one of the issue, that how small we can make these devices. So since the stress anisotropy is dependent on the volume of the magnet, that is the omega, we do need to consider the have some volume, right? So the way we can increase the volume, we can reduce the cross sectional area and increase the thickness, right? That is how we can do. So there has been some simulation results on that, and then but they still there is a need how we can do more. Like, so that is how the antiferromantically coupled nanomagnets at low dimension, that is a recent development. So here what we have shown that in the presence of correlated noise, because these two nanomagnets are very nearby, so we are having an exchange coupled layer between the two nanomagnets, and they are exchange coupled. This is called indirect exchange, well known inductance exchange, that is archic wire interaction. So these two magnets will experience very same noise. That's why they are called correlated noise. So with correlated noise, it turns out that these are very highly stable. The mean deflection decreases. Deflection is decreasing means stability is more. So we did some stochastic LLD simulation to understand that. So that's why it is very highly stable. So you would like to explain this, why it is. So the first panel shows that two magnets, they are not coupled. Exchange coupling is zero. So in that case, we got a very nice 20 kT energy barrier. So it shows that we are good. Simulation is good. Now we have put some exchange, experimentally feasible exchange coupling. So here we see that with the exchange coupling, this distribution is becoming narrow. It means they are less fluctuating, and that is equivalent to improved energy barrier of 60 kT. And even if you can do it more in exchange coupling, then you are getting even higher energy barrier. So it means that we can reduce the dimension of the uh, magnets even smaller and smaller we can go, and then we can have like we can make it like 40 kT energy barrier. So it is possible to go less than 10 nanometer. So the explanation was very exotic. It has been shown that that if whenever two antiferromagnets they are coupled, the in the presence of correlated noise, it counters each other, because one magnet tries to go from the stable position, other magnets try to counter that, and that is all the directions. If you try to point it out, and it is there in my paper, that that gives you the high stability. For ferromagnetically reason, ferromagnetically coupled, these things do not happen. So that's why antiferromagnetically coupled is preferred than the ferromagnetically coupled, as long as the stability is concerned. So we have done some more simulation on this. So we are not in the interest of time, I will just keep that. So we'll now talk about the experimental works. So in our experimental process, initially we deposit the materials using RF magnetron sputtering that can go to nanometer regime, and then also for patterning we use electron beam lithography. Then for material analysis, we do X-ray diffraction and energy dispersive X-ray spectroscopy. For thickness measurement, we do scanning electron microscopy, tunneling transmission electron microscopy, and X-ray reflectivity, ellipsometry, atomic force microscopy. Several things we can do. I'll show some results on XRR and ellipsometry. And for device characterization, there are several instruments that we use. For experimental automation, we use the LabVIEW, and for data analysis, we use programming languages and also Origin, and for some other stuffs, we also use COMSOL for finite element solver. So in device characterization, we use 4-probe method for electrical characterization. For magnetic characterization, we use electromagnet, magnetic thermal annealing, vibrating sample magnetometer, magneto-optical core Kerr effect, ferromagnetic resonance that I will be talking about, that what we have done, magnetic force microscopy, tunneling magnetoresistance. In piezoelectric, we do that also I will talk about today, that we have done some kind of nanoscale displacement measurements for piezoelectrics. Particularly, we use fiber optic sensor that is very highly sensitive, and other things are there like strain recorder, strain amplifier, so that we can go to we can measure very small dimension change. And also we do piezo response force microscopy to understand the surface morphology. Okay, this is more or less the experimental methodology that we will be employing. That is the electron beam lithography. We can fabricate like multiple pillars that will be individual beats basically, and we can do also, we need to do also perpendicular anisotropy magnets. And there are some stuffs I will be discussing in detail. So we do magnetic thermal annealing for stabilizing the system, and yeah. So here it is like a sputtering machine that we have used. There is a vacuum chamber. It can go to like 10 to the power minus 7 torr. There is a DC power supply, RF power supplies. So that can be useful for depositing metal and the insulator respectively. And there is a lab view controller with PC that can control this process. Plasma is formed in between inside the chamber, and there are different colors for depending on the materials. There are these are the main chambers here, and here there are multiple materials that you can deposit one top of another without breaking the vacuum. For example, for multiferric composite, we need to deposit two material that are in intimate contact, right? So we need to uh, use that vacuum for without breaking the vacuum, multiple layers we need to do. So here, these are the things that we have deposited, like PMNPT piezoelectric layer. We have deposited like 25 nanometer minimum, and we have also deposited more. And so more thicknesses. Iron gallium, we have deposited less than 5 nanometer, and some other standard cobalt FeB, those kind of standard materials that also we have deposited for characterization first. Here is the magnetic thermoannealing setup that we have developed here inside our lab. So there has been electromagnet, and then there is a furnace. That furnace can go to like 500 degrees centigrade. So in magnetic thermoannealing, we need to apply very high temperature, magnetic field, and also under vacuum, right? So all these things that we have done in between, we have done it, and then we have to place this thing in between a electromagnet poles to have the applied magnetic field. Okay, so it can go to like 400 degrees centigrade, and there is also vacuum pump. There is a vacuum pump that is connected to the hose pipe, and then it creates a vacuum. So under vacuum, we need to annihilate basically. So that is when it can go to it can be very stable, and it can give us the stable output. And yeah, so here is the results that after before and after magnetic thermal annealing, we can see that the almost 20 times area has been increased. So we use Quid VSM for very sensitive measurements of hysteresis curves. After MTA, we got the MS equal to 1.43 Tesla. Here we see that there is some hysteresis curves that is showing, but these are happens because of the silicon wafer is diamagnetic. When magnetic field increases, it decreases, magnetation decreases. So we have to negate that effect while resulting while working on the only the magnet. So we have also done magneto-optical Kerr effect for hysteresis measurement, and so there are different magneto-optical Kerr effects that we can do, and we have done it. Now for material analysis, we have done X-ray deflection, XRD. So here we can get on top of silicon wafer, we have deposited iron PMNPT, and we have deposited here iron gallium. Okay, and this is the PMNPT peak that we are getting. Silicon is crystalline, that's why we get a very nice peak for both the cases. But for iron gallium and PMNPT, these are sputtered deposited, and they are more like polycrystalline. So that's why we are getting very broad peak and also noisy peak. But it shows that there are some materials that have been deposited. All right. So now to understand that which materials have been deposited, we have done EDAX, energy dispersive X-ray analysis, that is connected to scanning electron microscope in our institute. And here we see that all these materials, iron, gallium, all the peaks we are getting here. So it means that we have been able to successfully deposited the materials, and there is no contamination. We did not get much contamination. Now after that we need to really see that whether thicknesses have been deposited properly. So PMNPT, for example, or iron gallium, or even bilayers, we have done XRR, X-ray reflectivity, that can give the fringes. And you see that for the bilayers, we are getting two sets of fringes, and it shows very clearly there are bilayers are there. And similarly for ellipsometer also we have utilized for different single material and also multiple material, and from there we can do the data analysis and individually calibrate those thicknesses, particularly at lower dimensions. We'll do. After that, we have done important measurement, that is like ferromagnetic resonance. So in ferromagnetic resonance, we have to keep the magnet rotating. So that's why we need to put a RF magnetic field that acts as a negative damping. So this is the like Lorentzian, this is the resonance, and this is the derivative of the Lorentzian. And for the magnetic field and alpha, there is a simple relation. That comes from the FMR theory. So we can calculate the alpha. So here is this schematic diagram of the setup that we have done. That we have an waveguide. On waveguide there is a sample from the microwave generator, RF signal generator. It is coming to the sample, and from the output of the sample is going to the Schottky diode, and it is going to lock-in amplifier. Lock-in amplifier is used to noise cancellation, and from there we get a reference signal, and that is connected to the Helmholtz coil to modulate the signal. And there is a Hall probe for and Gauss meter for magnetic field measurements, and all these things are connected with PC LabVIEW set up in a PC to control and automate the process. So here all the instruments that we have used. First is coplanar waveguide, on top of which we will be putting sample. Then we have a DC precision power supply that can put like less than zero point 0.1 millitesla. And then we have this electromagnet Helmholtz coil. Lock-in amplifier is a particular important thing for noise cancellation. RF signal generator, nano voltmeter, so that this is a very precise instrument. And then there is a spectrum analyzer, and particularly Schottky diode that is used to rectify at high frequency, and that we have also our lab mate. So here is the full experimental setup. Here the full experimental setup is on a vibration tolerant table for noise cancellation. Here is the PC with LabVIEW setup, and this is the electromagnet coils, and there is a chiller for electromagnet to keep it cool. There is an Helmholtz coil over which we will be putting the lock-in amplifier signal, and this is the waveguide with sample. There is Hall probe with Gauss meter here. Lock-in amplifier and Schottky diode is connected from the output of the waveguide. These are the microwave coils and RF signal generator through which we have done this, propagated this each RF signal, generated the RF signal for that acts as a negative damping. So here is the ephemeral lasers, and this is the derivative spectra that we have gotten. You see that we have been able to detect the signal of 10 to the power minus 5 compared to 10 to the power minus 6. 10 to the power minus 6 is quite the noise floor, but we have gotten a very nice fitting with this setup, and from there we can calculate the alpha is 0.0042. Then we have worked on some nanoscale displacement measurement. So here we have talked about, we have worked on D31 coefficient. It means that in the one direction, say X direction, you are putting electric field, and the third direction, Z direction, vertical direction, you are measuring the displacement. We have used the fiber optic sensors for this. So this is the complete setup here. Here you see that fiber optic probe is put on the sample. There are two contacts, and the both sides, two contacts have been generated using a silver paste and hot plate, and then we have calibrated the fiber optic signal for PMNPT, this piezoelectric wafer. We got an expected curve on this, and there is a sensor mounting block and all sorts of precise things to make it very stable. And this is the this displacement measurement system control interface. Here it shows the displacement, and displacement we have been able to measure like 50 nanometer for a voltage of 300 volt, and it turns out this D31 is 1666.67 picometer per volt. Similarly, we have done a very precise measurement for D33, that is the applied voltage is also in the Z direction, and measured strain is also along the Z direction. So we have a displacement sensor for that. This displacement, the inset shows it is very touching the sample where we are applying the voltage. So we are using a high voltage power amplifier to generate 1000 volt, and this displacement it has been able to detect like 3 micrometer, and we are getting D33 about 3000 picometer per volt. There is also a separate D33 meter, but it has some problem with the very high D33 measurement. So that's why we have made this setup. There is also strain recorder, strain amplifier to help these things, and also we do polling of the wafer, so that these dipole moments they align in the same direction before these measurements. Also, we have worked on the magnetostrictive coefficient measurement. So here we are putting magnetic field, and on the sample we have used like iron gallium as a magnetostrictive magnet, and these things we have varied this signal magnetic field from 1 millitesla to 1000 millitesla, and we see that we are getting very nice repetitive patterns. So it shows that there is strain is getting increased. So the displacement that we have been able to measure, that is 0.4 micrometer. With the D31 coefficient for iron gallium, it is like 4 micrometer per Tesla. That is what we have gotten, and all these things are software controlled using LabVIEW. Okay, so in the interest of time, I will quickly just summarize the spin devices part. So here we have shown that energy efficient spin devices using the simulation, and then antiferromagnetically coupled nanomagnets also can give the stability, area efficiency, and fastness of the switching speed. So many different fabrication and characterization things we have done. So damping measurements will be useful in the magnetization dynamics. Nanoscale displacement measurements also we have done. So this comes to me now that spin circuits. So in the spin circuit is a very versatile paradigm for analyzing the spintronic devices. So the main concept is that can you use very same types of circuit laws for spintronic circuits, the same thing that we have used for traditional transistors. So for these traditional transistors, there is a charge only, but for spin we have like direction also. So that's why there is a three direction like X, Y, Z. So it's like in general four component matrices for spin. So giving an example that how we can model those things. So we can any phenomena or materials we can model using corresponding components, and then we can attach them without worrying about the boundary condition. That is a very important thing, and this is very useful to conceive at also undergraduate level. Otherwise, it is spintronics is very advanced subject. So I also teach a course on spintronics and nanomagnetics, also on nanoelectronics here. So there, this undergraduate level, this spintronics is, for different exotic materials and phenomena that are coming, experiments are also very challenging. So rather than that, if you have some sort of spin circuits for that, and then for spintronics characteristics, usually it is possible for without knowing the exotic physics also, it is possible to determine the characteristics. That is one of the critical point. So for spin circuit, I just wanted to show that there is a difference between the normal charge based circuit and the spin circuits, where there is a spin ground, because spin relaxes due to spin diffusion. So if there is some up spin there, after traveling for some time, it will become randomly oriented. So that's why there is a called spin ground. And after solving this diffusion equation, you will get a very nice equation like tan hyperabolic cosine hyperabolic of this G1 and G2, these conductances. Okay, so I am not going into all the details of this. So one can formulate these very different magnets for magnets, interfaces, everything one can devise. And then there is a spin pumping mechanism where that is what we are modeling here. That in spin pumping means there is a ferromagnetic resonance, then it will pump the pure spin current without any charge component along the adjacent materials. And there is scattering formalism for this, how to get these interfacial conductance matrices, all these things. So that also modifies the LLG. For example, it can increase the increase the damping coefficient, and also there is a shift in resonance. So that happens because for the magnetic insulators, for magnetic metallic magnets, imaginary part is not big enough. So but for magnetic insulators it is important. So I will just go through quickly on this in the interest of time. So it has been shown using this circuitry that interfacial uh, uh, voltage sources, they get cancelled out if you model those things properly. And this is the phenomena also people have observed, that spin battery that appears at the only the interfaces, not at the internal elements in the material magnet. So these are the things that we have been able to formulate the equations that to interpret the experimental results for very many different materials and phenomena. For example, for permanent platinum, we have been able to also address some of the controversies. For example, lambda, some of the papers they have used like 10 nanometer. So there is a lot of controversy on this. So, but it shows that there is some upper bound that you can use. Otherwise, the conductance will become negative, right? So that has been also used to, determine the material properties from experimental results. Say, for example, for in let me skip this. So for example, there is a spin diffusion length. There is a very controversy in literature. So you see that there is a it is reported like zero point 0.5 nanometer to 14 nanometer, and there are many problems in this, that what are the temperature may be an issue, lambda, particularly this lambda proportional to sigma, that is the issue. That is also, there is a spin memory loss, so those kind of things are there. So we have worked on those things, and there is a critical issues that have been pointed out, particularly for interfacial or effective spin mixing conductance and inverse spin Hall effect. They saturated two different dimension, and it shows very clearly that lambda proportional to sigma, LE, that corresponds to area on TFH spin relaxation mechanism. And there are many other things that we have done, particularly also for magnetic insulators we have worked on. That things are very very complicated, but if you do it in a proper manner, then one can get nice results. And particularly, for example, there is a kind of kink that happens, that does not happen for metallic magnets, but for it happens for insulating magnets, because there is a imaginary part of conductances. So those are, there are many qualitative phenomena that have been experimentally, that have been observed, that have been, we have been able to explain those things. Also, we have done worked on spin torque ferromagnetic resonance, and I'm not going into details, but those things are very useful for this complicated equation that can be useful. And we can use some netlist to write those, just solve these things using this netlist. We need to just write that as an user, and after that, in any complicated devices, one can model and get the results and match with the experimental results. Okay, so now it lands me the just a couple of minutes. I'm just trying to finish. So here we are talking about spin circuit. That is a recent development last year. The spin circuit representation of spin pumping into topological insulators. So in topological insulator, the number of articles is and citations are increasing a lot over the time. So it's a very exotic material where surface is conducting while the bulk is insulator. Okay, so we have developed some spin circuit models on this, and experimentally, that is very interesting curve, that with thickness, bismuth selenide is a topological insulator. With bismuth selenide, the thickness, the it resistance decreases. So that is a wrong thing, right? Because if it is Ohm's law, then with thickness, resistance should always increase. But it happens because of the, whenever the thickness is increasing, then there is a, the two surfaces are they are separated by more length, and they are giving you the signal. So that is why this interesting thing comes from the surface states. So we have modeled these surface states, and using this modeling, we have been able to show that these experimental results, we have been able to match it, and we have shown that, well, it certainly comes from the surface states of the topological insulators. And also, we have been able to solve some controversy in literature, that is called Onsager's reciprocity. Many people have used like theta sh, that is the spin to charge conversion, that is greater than 1 for topological insulator, but we have shown that it is not possible. It comes from the simple energy conservation. Like if you have a charge current that you are converting to spin current, and then again you are converting it to charge current, then it will pick up a theta hs and once, and here also theta hs once, right? So it will give you theta hs curve less than equal to 1, and it will definitely give you less than. So theta hs can be also negative, depending on the, say for example, platinum and tantalum, they have a different direction, and there are physics on that behind this. So it solved the controversy quite in the literature. And we have also proposed some of the interesting device structure, like using a spin sink layer. It is possible to increase the inverse spin Hall voltage, so that there is a backflow of spins that can be reduced by using a spin sink layer, that magnet can access a spin sink layer. And using this technique, you can always put some numbers and see that how much it will be useful, and later on you can measure the, you can match the experimental results. Okay, so this brings me to the summary of this. So basically, we are putting the physics to devices correctly, so that it is possible to interpret the experimental results. And also for large scale circuit, it is very important that that is not possible to use using boundary conditions at different interfaces. We must use the circuit solver for this. And so thank you very much. If you have questions, you can ask, or you can also write to me. So I want to last acknowledge the group members of my lab and experimental facilities. And this work was also supported by different grants from Science and Research Engineering Board of India, and also I have Quantum Technology Foundation by DST, Department of Science and Technology. So now I'll be happy to take questions. Thank you.